In our previous module 2, we have discussed about the solution of the homogeneous linear equations, the autonomous system, where we have considered the eigenvalues to be real and distinct, and also we have considered the case where the eigenvalues are complex. In this module 3, we will look into the case when the eigenvalues are equal. We will also discuss about the generalized version where we have k linearly independent solution which is less than n. We will now consider the solution of the homogeneous equation where the eigenvalues will be equal. If the characteristic polynomial of A does not have n distinct roots, then A may not have n linearly independent eigenvectors. So, in this example, we consider three different matrices A, B and C. Each one is having the same set of repeated eigenvalues, but number of linearly independent eigenvectors are different in each case. Let A, which is also equal to I, that is the identity matrix, be taken as 1 0 0 0 1 0 0 0 1. It is easy to check that A has three repeated eigenvalues lambda 1, lambda 2, lambda 3 is equal to 1, and you do that by taking this as A minus lambda I equal to 0, and you get the determinant values to be 1, 1 and 1, and hence in this case theorem is not applicable, but still we can find three linearly independent eigenvectors, namely 1 0 0, 0 1 0 and 0 0 1, which we name as V1, V2 and V3. We now consider a different matrix B, a modified version from A, which is given as B equal to 1 1 0, 0 1 0, 0 0 1. So, the only addition is this number 1, which was 0 in case of matrix A. Here also it can be easily checked that B has three repeated eigenvalues lambda 1, lambda 2 and lambda 3 all equal to 1, but this time we can find only two linearly independent eigenvectors given by u1 equal to 1 0 0 and u2 equal to 0 0 1. A little modified version of A we again consider and name it as matrix C, which is equal to 1 1 0, 0 1 1 and 0 0 1. So, the difference from matrix A is that this number and this number, both of them were replaced by 1, which were zeros in case of matrix A. Again, we can check the eigenvalues of the matrix C, which is lambda 1, lambda 2 and lambda 3 is equal to 1, but in this case we can find only one linearly independent eigenvectors given by W1, which is equal to 1 0 0. So, if we consider the following three linear system of equations, x dash equal to Ax, x dash equal to Bx and x dash equal to Cx, where x dash is dx dt and A, B, C are matrix defined above in this example, then we have respectively 3, 2 and 1 linearly independent solutions of the form e to the power t into z, where z is a constant vector. So, in the case of equal roots, we need to adopt some other method to find the general solution. We now discuss the general solution. Suppose the matrix n cross n has only k linearly independent eigenvectors, where k is less than n. Then the vector differential equation is given by 1 which is dx dt is equal to Ax, and it has only k linearly independent solutions of the form xt equal to e to the power at into v for every constant vector v. Now, our task is to find the remaining n minus k linearly independent eigenvectors. So, taking motivation from the scalar case, we may try xt is equal to e to the power at into v as our solution. Let the matrix A be an n cross n matrix, then the function e to the power at may be defined as e to the power at is equal to I plus at plus a square t square by 2 factorial plus dot 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 plus a to the power n t to the power n by n factorial plus dot 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 given by equation 2. Please note, this is just an expansion of e to the power t. The only difference is here A is a matrix, and hence instead of 1 this is replaced by I, the identity matrix. It can be shown that the infinite series 2, which is actually the expansion of e to the power at, it converges for all t. In fact, the following inequality is true, that is, norm of e to the power at is less or equal to e to the power norm a into t for each fixed but arbitrary t. Since the last inequality shows that the convergence of the series 2 is uniform, the series can be differentiated term by term. So, in particular, when we differentiate e to the power at with respect to t, we will get ddt of e to the power at is equal to a plus a square t plus dot dot plus a to the power n plus 1 by n factorial t to the power n plus dot dot dot. Please note that actually you are differentiating this expression too. So, if you differentiate this with respect to t, this term will be 0, this term will be a, this term will be 2t, and that 2 cancels with this 2 factorial, and this term will be a to the power n, n t to the power n minus 1, and the next term will be a to the power n plus 1, n plus 1 t to the power n divided by n plus 1 factorial, and this part is actually given here. So, if you now take a common, you will get this is equal to I plus a t plus dot dot a to the power n by n factorial t to the power n plus dot dot dot, and this whole thing is nothing but the expansion of e to the power at, and hence we replaced this whole expression by e to the power at. Therefore, we conclude that ddt of e to the power at is equal to a e to the power at. That is, e to the power at into v is a solution of 1 for every constant vector v. Since ddt of e to the power at v is equal to a e to the power at v is equal to a into e to the power at v. Theoretically, x t equal to e to the power at into v is a solution of the system of linear differential equation x dash equal to a x, but practically finding the infinite sum in e to the power at into v for any arbitrary square matrix A is not an easy task. So, now we show how to find n linearly independent vectors v for which the infinite series e to the power at into v can be turned down to a finite series and can be summed exactly. Please observe that we can write e to the power at into v is equal to e to the power a minus lambda I into t multiplied by e to the power lambda I into t into v, such that e to the power lambda I t and e to the power minus lambda I t, both of them cancels each other, and we will get e to the power a t into v for any constant lambda, as a minus lambda I into lambda I is equal to lambda I into a minus lambda I. It can be proved that e to the power a plus b is equal to e to the power a into e to the power b, which is equal to e to the power b into e to the power a when ab is equal to ba. Moreover, e to the power lambda I t into v is equal to I plus lambda I t plus lambda square I square t square by 2 factorial plus dot 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 into v, which is equal to 1 plus lambda t plus lambda square t square by 2 factorial plus dot 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 into v, which is equal to e to the power lambda t into v, and hence we conclude e to the power a t into v is equal to e to the power lambda t into e to the power a minus lambda I into t into v. Now, we give the method by which we have a scheme for finding n linearly independent solutions, and hence the general solution of 1. So, first we find all the eigenvalues and eigenvectors of the matrix A. If A has n linearly independent eigenvectors, then the differential equation 1 has n linearly independent solutions of the form e to the power lambda t into v. But suppose A has only k in linearly independent eigenvectors, which is less than n. This means not all eigenvalues are distinct, that is, some of the eigenvalues are repeated. So, we have only k linearly independent solutions of the form e to the power lambda t into v. Here we recall a result of linear algebra that the number of linearly independent eigenvectors, which is also called the geometric multiplicity, in short GM, cannot exceed the number of repetitions of the corresponding eigenvalues, which is the algebraic multiplicity, in short AM. So, to find additional solution, we will pick up only those eigenvalues of A for which the algebraic multiplicity is greater than the geometric multiplicity. Let lambda be such an eigenvalue of A, and we find all vectors v for which A minus lambda I square v is equal to the null matrix 0, but A minus lambda I into v is not equal to the null matrix 0. For each such vector v, e to the power a t into v is equal to e to the power lambda t into e to the power a minus lambda I into t into v. So, please note here minus lambda I t and e to the power lambda t, they cancels each other. I is the identity matrix and acts like 1, and this we can write as e to the power lambda t into v plus t times a minus lambda I into v, which is an additional solution of 1. We do this for all such eigenvalues lambda of A for which the algebraic multiplicity is greater than the geometric multiplicity, in short AM greater than GM. The aim is to find AM minus GM number of remaining solutions. If we still do not have enough solutions, then we find all vectors v for which a minus lambda I cube v is equal to 0, provided a minus lambda I square v is not equal to 0. For each such vector v, e to the power a t into v is equal to e to the power lambda t into v plus t into a minus lambda I into v plus t square by 2 factorial a minus lambda I square into v is an addition solution of 1. We keep proceeding in this manner until we have n linearly independent solutions, that is, for eigenvalues with the algebraic multiplicity is greater than the geometric multiplicity, and we have additional am minus gm number of solutions obtained by the above procedure. We have just discussed the solution of homogeneous equation where the eigenvalues will be equal. We have also given a general procedure of how to calculate the solutions or how to conclude about the solutions of the homogeneous equation when you have k linearly independent solutions which is less than n. We will now take an example which will be clearly explaining this situation. We will now state a lemma which will guarantee that the previous explained scheme will work. So, the lemma is as follows: let the characteristic polynomial of the matrix A have k distinct roots lambda 1, lambda 2 dot dot lambda k with multiplicities n1, n2 dot dot nk respectively. Suppose A has only Vj which is less than Nj linearly independent eigenvectors with eigenvalue lambda j. Then the equation A minus lambda j into I square V is equal to 0 has at least Vj plus 1 independent solutions. More generally, if the equation A minus lambda I into I whole to the power m v is equal to 0 has only mj which is less than nj independent solutions, then the equation A minus lambda j into I to the power m plus 1 v equal to 0 has at least mj plus 1 independent solutions. We take this result without proof and we look how we can apply this in an example. So, in this initial value problem, we have the equation dx dt is equal to Ax, where A is the matrix 2 1 3 0 2 minus 1 0 0 2 with the initial condition x 0 is equal to 1 2 1 given by equation number 3. The characteristic equation of this matrix A by definition is given by determinant of A minus lambda I is equal to 0, where I is the unit matrix 1 0 0 0 1 0 0 0 1, and if you do that you will get the determinant 2 minus lambda 1 3 0 2 minus lambda minus 1 0 0 2 minus lambda equal to 0. And if you expand the determinant, you will get 2 minus lambda cube is equal to 0, which means you have a repeated value of lambda 3 times, and hence lambda equal to 2 is an eigenvalue of A with algebraic multiplicity 3. So, by algebraic multiplicity you mean that the number of repetitions of the eigenvalue, and in this case it is 3, and hence the algebraic multiplicity is 3. To find an eigenvector corresponding to the eigenvalue lambda equal to 2, we have the same following procedure. We have A minus 2I into V is equal to 0. After simplification, this is going to give 0, 1, 3, 0, 0, minus 1 and 0, 0, 0 into V1, V2, V3 is equal to the null matrix 0, 0, 0. Now, this implies V2 and V3 is equal to 0 and V1 is arbitrary. So, you choose an arbitrary matrix 1, 0, 0 and we can conclude that x1t, the 1 denotes the first solution, is equal to e to the power 2t into 1, 0, 0 is the only non-zero solution of x dot equal to at. Thus, A has only one linearly independent eigenvector for lambda equal to 2. That is, for lambda equal to 2, the algebraic multiplicity AM is 3 and the geometric multiplicity GM is 1. So, by geometric multiplicity, we mean that the number of linearly independent eigenvectors, which in this case is 1, and that is our AM is greater than GM. So, in order to adopt the described scheme, we have to find the remaining 3 minus 1 is equal to 2 solutions. So, this 3 minus 1 is coming from the difference of the algebraic multiplicity and the geometric multiplicity. We next consider the equation A minus 2I square u equal to 0, and this gives 0, 0, minus 1, 0, 0, 0, 0, 0, 0 into u1 into u2 into u3 equal to the null matrix 0, 0, 0. This implies u3 is equal to 0 and both u1 and u2 are arbitrary. Please note, if I multiply this, I will be getting 0 into u1 plus 0 into u2 minus 1 into u3 equal to 0, which will give me u3 is equal to 0 and u1 and u2 are arbitrary, because from these two equations, that is 0 into u1 plus 0 into u2 plus 0 into u3 equal to 0, we cannot conclude anything about u1 and u2. So, we have this conclusion that u3 will be equal to 0, where you can choose u1 and u2 as arbitrary values. So, now we choose the vector u equal to 0, 1, 0. Please note, this u3 will always be 0 and you can choose anything between 0 and 1 which satisfies A minus 2I square V equal to 0, but A minus 2I into V will not be equal to 0. And if you get such a vector, we will be having our second linearly independent solution as x2t, this 2 denotes the second solution, is equal to e to the power at into 0, 1, 0. And this can be written in the form e to the power 2t into e to the power a minus 2I into t multiplied by the matrix 0, 1, 0, which is equal to e to the power 2t into the column vector t, 1, 0. And this is our second linearly independent solution of dx dt equal to Ax. Since the equation A minus 2I square V equal to 0 has only two linearly independent solutions, we do one more step of the scheme and find all the solutions of the equation A minus 2I cube into W, which is equal to the null matrix 0, 0, 0, 0, 0, 0, 0, 0, 0 multiplied by the column vector W1, W2, W3 is equal to 0, 0, 0. It is clear from here that every vector W is a solution of this equation, and hence we choose a vector arbitrarily W equal to 0, 0, 1, which is a vector which satisfies a minus 2i cube v equal to 0, but a minus 2i square v is not equal to 0. Please note that you can choose any arbitrary vector w here which satisfies these two conditions, and it is going to be another linearly independent solution. Hence, x3t, where 3 is the third solution, which is equal to e to the power 2t e to the power a minus 2i into t multiplied by the column vector 0, 0, 1, which is equal to e to the power 2t into I plus t into a plus 2i plus t square by 2 into a minus 2i square multiplied by the column vector 0, 0, 1, which after simplification gives e to the power 2t multiplied by the column vector 3t minus half t square minus t 1 given by equation number 8, and this is our third solution, third linearly independent solution corresponding to the eigenvalue lambda equal to 2. Hence, the general solution of the equation 3 is given by xt is equal to c1 x1t plus c2 x2t plus c3 x3t, where xit I equal to 1, 2, 3 are given by the equations 4, 5 and 6 respectively. Using the initial condition for this problem, we will get c1 is equal to 1, c2 is equal to 2 and c3 is equal to 1, and hence our required solution is xt is equal to e to the power 2t multiplied by the column vector 1 plus 5t minus half t square 2 minus t 1, which is our required solution of the initial value problem 3. In this module 3, we have discussed about the solution of the homogeneous equation in the case of equal roots, that is when the eigenvalues are equal. We have also given a general scheme to how to calculate the solutions when there are k linearly independent solutions which is less than n. In our next module 4, we will discuss about the fundamental metric solution, which is another important aspect of the higher order differential equation. Thank you.